So with a great pleasure, I'm happy to have Sadaf opening the day with a real session. Not that we didn't say important things, but so Sadaf's going to talk about mapping X as a service model on Petascale supercomputing ecosystem. Welcome, Sadaf.
Thank you for inviting me. And I didn't look back because I came late last night. I think it's probably third, fourth time I'm giving a talk at the session, if something like that. I think I did most of them, not all of them, but yeah. So there is no HPC in my title, and there is no AI in my title, unfortunately. But I have supercomputing, and so I think it kind of maps. But I think it's important for us, and I will try to convince you in the rest of my talk, why we have to now start looking at this as a service model, which is, I think, a loaded and an overloaded term in the context of our community. And it's kind of a technical vision we have at the center, CSCS. So as a full disclosure, this talk is almost 70% of a talk I gave at an event which is called International Workshop for Advanced Computing and Analysis Techniques in Physics Research. So this is, if I oversimplify it, is a research conference that is mainly organized by researchers and technical teams at CERN. And they invited me and they said, can you come and give us a talk about HPC friendliness? And you might ask, what does it mean? So as I was preparing, and that's the title I chose, because I think you can look at friendliness in many different ways, but in the context of this community, which is high energy physics community, you can associate them with the computational grid that started in early 2000. And as we are looking at the AI, machine learning, and deep learning aspects, what people want. So I pretty much boiled it down to interactive, on-demand, and bespoke services. And I'll go into detail a little bit later. And there I chose the keywords like cloud technologies or what. So you can probably start seeing a little bit of a theme. But as I was thinking about it, I said, okay, how does a friendship kind of look like between a physicist and an IT person? And then I started getting some weird ideas, so I just used a picture, how in general a friendship looks like. But you will see some theme of that going back. So you're here, and some of you have been here probably more than once. So I don't want to introduce CSCS, what it is, what it does, but I want to introduce it in a manner that you can relate how we are an innovative, forward-looking center which really likes to work and engage in the community in collaborative work. So we have a mission, of course, as a center, and we have some infrastructure really forward-looking and innovative, and we provide a set of services which are always increasing and expanding. So, sorry, I'm looking less to you and more to my screen because I can't read from here, and I have to look back, and there is nothing to look, So, as you can see, we provide high-performance computing technologies to our researchers and scientists. And this is a very, very fast-moving field, as you could imagine. And that's why it's very interesting. So if you are, in doing so, in order to be very environmentally friendly and sustainable, we have a very innovative data center infrastructure with a rather unique and innovative cooling system. So I don't know, Hussein, is there going to be a data center visit this time or not? No, but in case you haven't been there, just ask around one of my colleagues and they can give you more details how things work, and even can take you there. It's like not that far away from here. You heard some of our infrastructure is big. Yeah, many, many thousands of GPUs, CPUs, a very fast parallel file system side by it. So, I'm playing it down, but it's quite impressive in the sense I don't want to, toot my own horns in some sense. But we have a rather unique and innovative computing or IT infrastructure. Using that IT infrastructure, so it's not technology for the sake of technology. We provide a set of supercomputing services. On these systems, we provide a set of data services in our environment. And in the past couple of years, we started offering some cloud technologies, and I'll come back to that later. And as I said earlier, of course, we always talk about technology. I personally always like to talk about technology, but why we are doing it? We are doing it for our users and customers and who they are. So in a large way, they are mainly selected from a process called user lab. And people who came from, for instance, US, you can kind of think of it as from a DOE point of view inside or from a NSF point of view exceed. So it's an open competitive call. Scientists don't have to pay anything, and then if their proposals are successful on scientific merit, they get time on HPC systems. One of our most important customer, and they have their own system because of their own operational needs, is Meteosys, the weather forecasting. Then we have other customers, as it was written, CHIPS, so it's high energy physics community. The reason I highlight it because one of the use case and evidence of how we are mapping system services to our high-end system, you will see them over and over again. And we are lately participating also to European infrastructure projects, research infrastructure projects. So if you go to CSCS website, you can see science highlights. There are many of them you can find on our website. The other thing you see from a Meteosys weather supercomputing system, I think up until recently, the IBM announcement, we used to be the only production, Meteosys, together with Meteosys, was the only system that was doing weather forecast, operational weather forecast using a GPU-based system. On our main flagship ecosystem, what we do is we try to consolidate as much as possible on the same infrastructure, and you will see how and why, and I think I would say it's becoming more and more important. So most of our customers and users, when they want to come and use HPC resources, including compute and storage, we don't build unique environment for them, but we rather map them on an existing infrastructure. For them, it is cost effective for them, and also it's cost effective for us in terms of scaling our CapEx and OpEx. Again, a little bit of marketing here, but what you can see is as we are growing PISDA, and it's not only growing in terms of capabilities, in terms of flops and more flops and more flops, but we are making it more versatile. What does it mean? It means that in addition to, of course, the interfaces which you have through SSH or batch job submission and file transfer, what we do is we try to exploit that in mapping similar customers and ecosystems. So on your right side, what you see are a number of customers in addition to user lab. They are running services in the PISDA environment. And if you recall, one of the reasons we have a heterogeneous system in terms of GPUs and CPUs and multi-core within a single network fabric is to allow them to map different type of workflows coming from these communities. And we added a little bit more technical capabilities to accommodate that. So this is a slide I'll spend a little bit more time on because it will come back again at least one more time. So if we look at a service model, so we are offering HPC as a service, we are offering compute as a service. And again, you can map them in different axes, but I chose two. So what you see in vertical, which being an HPC person for now close to 20 years, our value add or our differentiator is performance. No matter what we do, if we don't do it with high performance, then we are not doing a good job anyhow. So the key and the focus for us, no matter which technology or technological element we are talking about, or our competitiveness comes from delivering performance to our user community. But what is becoming more and more important is service programmability. What does it mean? So the way I view it is how much work you have to do, how much unique work you have to do to map something that is slightly different, not just in terms of technology, but also in terms of policy. For example, we have a policy for having 24-hour jobs on our design for most. But if a customer comes and they say, okay, by the way, I need something slightly different, how much work it is for us to accommodate a unique requirement in a given system. And my goal is, or at Center, the goal for us is we would like it to be as automated as possible as we see in the cloud environment. So one way you can view the lower part as automation. It doesn't mean that none of us will be eventually needed, but that's a thought you can sort of think about that. Yeah, once we are fully automated, we are all gone, and there will not be or HPC advisory council with bots. But I'm pretty sure there will be still work to do. But so if I look at it on the system, of course, our HPC system like Petascale is tuned and designed for performance. So we have a high performance file system, we have a high performance HPC system. And as long as you fit in the model of running bad jobs and doing faster, you can run not only well, but very well from day one on this environment. But for instance, if we offer, let's say, Media Swiss as a service, we offer a full appliance type of an environment to there, then we design a system pretty much mapped to their requirement, and then we end up having a separate cluster for them. Because their operational, their design requirements are so unique, we do something completely different from them. Then CHIP is this high energy grid middleware. It was such a unique middleware, you needed essentially a unique cluster for that. And it wasn't not quite possible to map all of them in a consolidated environment. Then we have a site-wide file system spectrum scale. And please, I would ask you not to look at these placement of these things as a relative to one or the other performance, like Lustre is not always very powerful and IBM Spectrum Scale is not always more programmable, but these are relative terms showing capabilities, not necessarily absolute design properties of these systems. And as we are going to more programmable services, we introduced OpenStack, which infrastructure as a service environment. Some of our customers for various needs are asking for Kubernetes, and we are going more and more programmable environment. But as things stand outside the box, they tend to be more programmable, but not as high performance as we would like. Again, performance could be a rather relative term, but coming from, one could say, a bare metal programming environment, they don't deliver the same level of performance that we would like. And then you see another logo for a research infrastructure there. So ideally, this is our vision. We would like to be where I have the question mark. I would like to be able to combine and scale out an ecosystem, whether it's compute and storage, which is very, very high performance, but also very, very programmable and as automated as possible. And ideally live in an ecosystem together with other distributed cloud ecosystem. So if you thinking of vision, this cloudy thing, I don't want to make a cloud system. I want to retain all the properties of a high performance system. just turning up gear a little bit just to give an idea, and I should keep track of it. So of course, we are very proud. We have a nice, shiny data center. We have a very fast. But if I look around what is happening in the wider community of, you can call it IT, it's quite humbling. So I picked up this information from, and the link is there. So they list like top 10 systems based on how much power they can have and how much floor space they have. So since in the top 500 list, we are number 5 system. So I just picked number 5 here, but you can go to the website and look at it. And if I just look at the sheer floor space they offer and the power, I mean, it's just mind-blowing. For a little while, I was a bit depressed. I said, oh my God, I mean, I feel so, useless in some sense. But, you have to look at it from this context point of view. So on a positive side, we are looking at an ecosystem where innovation is happening outside our community at a very, very fast rate. And we can really take advantage of it. But at the same time, we have to see what we do differentiates us. And what does it mean? Not differentiates us as a data center, but differentiates, provide a distinguished feature for our users and customers. Because the users and customers of these data centers are not necessarily the research scientists and federal mission agencies. Again, it's just more for an eye candy. So just you can see this, I mean, the term that is used is hyperscale data center market. And the take-home message here, again, I don't want to go and talk about what Google is doing and what, Alibaba and companies, because I mean, for me, the scales are just so enormous, I cannot, make sense of them. But the idea is this technical computing community is really growing outside an environment at a much, much faster rate than we have ever seen. So why do we care? This is why I care. No matter what we buy now, because there is a demand and supply issue, we are paying a lot. So any one of you who has done a procurement, like say, and if you have an opportunity to just look back in past, let's say 10 years, and even 5 years, what you invest, what you spend in terms of your capital expenditure, and what you gain out of it, it's not growing at a rate which you kind of used to just take for granted like 10 years ago. Because there is a demand and supply side of it. Maybe Gilad can tell how they are pricing or other vendors do that. But we as a customer, which tend to buy things from our point of view at a scale, we are seeing our capex cost increasing. If someone doesn't agree with me, please let me know that. If you think, oh no, we are getting a lot more for a lot less. So we can sit back and say, oh, what do we do? And it's all doom and gloom. But at the same time, I see it's an opportunity for us to rethink how we offer our services. I always tend, because of my role, I always tend to take a technical view. How, from a technology point of view, I could be either more frugal or more efficient. But I tend to take the view how I can enable our users, customers to do more with the same level of investment. So, just looking back and just reading some articles. In fact, on a plane, I watched a video on cloud computing on Lufthansa, for that matter. And I think the message there is this as a service model enable user. They give power back to the user. And when I look at it, we provide a very, I should not say simplistic set of service, but a very, very a small set of services to exploit HPC systems. And here I list them SSH, SPAT, SP. And with these tools, our users and customers were able to do a whole lot in past 20 years. So if you give them something, they really not only use them, but they really use to innovative and advanced research in their community. So I take a view, if we give them more capabilities, not in just of raw performance, which will be there, whether it's bandwidths and flops, they may end up thinking or rethinking of their problems and workflow in a completely unique manner. So what you see is that I would like the goal here is, of course, we would like to manage and lower our CapEx and OpEx in our data centers because of the market economy, but at the same time, while we are thinking that how we can use the same trends that are increasing our CapEx to empower our users. And it may look like, political speech where say, power users, but of course I'm a technical person, so I will translate into how we can use some key technological advances to combine the performance and programmability and automation side of things. So this is the focus and vision of the talk for me. Going into a little bit detail and say, what does this access as service means if I just do compare contrast? And it's not an absolute comparison. You can see it's a more survey type of comparison. So what do we do at HPC data center like CSCS? We offer performance and scaling as a service. What does it mean? Parallel computing, traditionally with MPI always. We have a very high performance parallel file system, so we can feed those nodes, typically POSIX based. We do typically this bulk programming, scale out with fast integrated fabrics, high bandwidth networking subsystem, both for compute, MPI, and for storage. And then typically our data centers are connected. Again, not comparing the sizes of public cloud, but rather high network connectivity to our other research centers. If I look in the cloud world, again, among many things, what I see, automation in the hand of users are there. And their user could be other enterprise users. And it's highly interactive compared to the way we provide our services. So if I look at infrastructure as a service model there, I typically look at it gives ownership of the infrastructure and related services in the hands of the customer, which we typically don't do for obvious reasons. I think I will be more or less, I should not say short at the spot here, but if I say, no, let's just give all the privileged access on PIS9 to our customers, I don't think anyone would appreciate that, including ourselves. Typically, okay. I thought I was offended someone by saying something like that. On demand, and you can equate it batch versus on demand. I have many discussions between batch and interactive batch, and interactive batch is not on demand. And I can go offline into that discussion more. High availability. And again, to me, this is not absolute. Of course, in order to make PIS9 more available, I can't make another PIS9, so that's out of question. But you can think of some key services being highly available. Role-based access control. So these topics are related because in order to do the one, you need the other. You need storage models. And the thing that maybe we can also benefit is isolation, security, and quality of service. Again, quality of service has many dimensions. So the goal for us is not to offer one at the expense of another. So now I will go, before I go there, because so far I haven't given any concrete, precise detail about anything. I talked about high-level topics which make sense, but as we all know, devil is always in the details, and once you start implementing and tuning a system, anything can go wrong, will go wrong, and more. So I'll talk you through a success story where we mapped a grid computing environment to a high-end HPC system. And it's a bespoke service. So the grid environment is not like any other standard middleware. And my colleague Miguel and others who have spent quite a bit of time here, they provided me. Just in case you don't know, I'm pretty sure most people know. So we have this Large Hadron Collider, and it has 4 sets of experiments that is north of Geneva. So very close to us, international collaboration, something to look at. Looking at their IT side, so what they have is, this is called worldwide high energy grid computing, and they have different tier side. I will go into a bit later what it means, but they're spread all over the world. And the idea was the way individual countries will get funding, they will invest in their IT infrastructure to process data that is coming out from the experimental facilities. And CSCS is a tier 2 site. So tier 0 is where they keep raw data. This data is very, very, very expensive to generate, so everything must be kept and then looked at and processed later. And then they go to tier 1 center, and as you can see, there are very well-defined roles for this tier 0, tier 1, and tier 2. And because of these very well-defined roles, they have a highly customized middleware, especially for tier 2, where they have this idea of compute and data federation, where from a user point of view, you don't really care where your data is computed is happening. So I'm going to now show slides that have been generated as part of this project over the past 2-3 years. So this was a collaborative project, as you can see. So Professor Christopher Grab, he is leading CHIP, this Swiss activity, and here he highlights this thing. So what is the challenge? The challenge for these experiments over the next 8 years, you need factor 50 more resources. And you might ask, what is the problem? It's always money. So they wanted to reduce their investment and operation cost, and they wanted to reach those level of compute and storage resources. So they said what we can do, and one idea was if we can move them from their own dedicated environment with their dedicated middleware and fold them into an HPC environment like Petascale, they will benefit from the scaling out of the resources as well as lower operation cost. So in 2016, we started this project called LHC on Cray. I mean, as you could imagine, we are very creative with names. And the idea was to see can we map that middleware on Petascale, and there were 2 sides of it. Can that community benefit from that and they don't want to make any changes to their user interface. So this migration should be totally transparent to their users. And at the same time, what was important for us, because Petascale is our flagship system, and we didn't want it to be at the expense of our existing user. So we didn't want a situation where by mapping that middleware and workload, our scalable jobs suffer and the storage suffer. So there were at least 2 sides to this story. And of course, there was a cost side, but I will not go into that. So this was a collaborative effort between them and us. And more or less, rest is history. They decided to go on this thing. So So in Switzerland, we done 3 of their 4 experiments on, so in fact, CSCS Tier 2 is rather unique in that environment. So this is the presentation that was done in fall 2017 HPCAC meeting. You can see the dates and other. So it's just a copy paste from that environment. And as you can see, the way the solution has been implemented, it's totally transparent to their VOs. And on Phoenix, it was their dedicated environment for the dedicated middleware. ARC is, I think if I can oversimplify, is the workflow management system that creates the abstraction for job submission and storage. And you can see PISDINE there. So from a VO point of view, up until we have the Phoenix cluster running, the jobs were transparently going to the 2 environment. And they had some other metrics and measures, like milestones, and the decision was due later half of the year. So, and from their point of view, again, this is a slide from the, not from us, but from the community. What did they see as we started this work? They say, the processor architecture and or OS may not be suitable. So essentially what it means, so grid middleware is a collection of many, many applications. And in order to keep some sense of portability, you can call them certify their applications again a given OS distribution. On PISDINE, that distribution, that OS distribution is not supported. So the idea was whether we have to rebuild and all these applications into PISDINE environment, and then would have been a huge overhead for us. Compliance with tight access rules. So they operate under their own grid certification environment, and the way we map their jobs onto an environment, they have what they call a single service account mapped into many, many other accounts. And their jobs are almost sequential, meaning that jobs would have to share single cores, in some cases, single hyperthreads. Application provisioning, so these were really big files, and the way they would access these files from the internet is more what we see in data science world. So you would like to have a network connection for individual HPC nodes, and if those of you who have built large-scale HPC system, typically your compute nodes do not have visibility and accessibility from the network. Workload management, integration, outright IP connectivity, that was a big, big requirement. And among all the other constraints they were bringing, one of the other constraints were they have a large number of very small files. So typically HPC storage is high bandwidth and low on metadata, and there was completely opposite. So they could kill luster like in seconds. But people work hard, and I will mention some key technologies that were used there. So as of beginning of March this year, all experiments are running in production on PISDINE. The dedicated cluster has been phased out. And this consolidated benefits users and customers. So in case if they have a requirement where suddenly they have to scale their cluster, on their old environment they would have to go through procurement and addition and certification. There, we can just give them a bigger partition on PISDINE environment if needed. So essentially, if I just boil it down to a very small concept, so essentially a high energy physics computing, which is a throughput computing in traditional sense of words, is running on a Petascale system without impacting the existing processor. So from an HEP community point of view or grid community point of view, PISDINE is a very friendly HPC Petascale system. And so they have these calls every 6 months. It's called Scientific Computing Forum, organized at CERN. And it's funny when I sometimes join in, they compare our system, PISDINE, with some other environment, mainly in the US, where they can run these workloads, but they have to really redo and redesign everything. And it was not easy. And so we learned a lot, we were successful, but this is not how we could do it going in future. So there are some results and observations. So the efficiencies are not impacted, even we are running single node jobs. And the most funny thing, this is what Miguel showed me, and this is what we were kind of expecting. Although the number of nodes, which are a fraction of PISDINE, I think it's a small fraction, it's like less than 5%. Because LHC jobs, they are high throughput jobs, they share cores within the job. Even in less than a month, you can see almost like 1/3 of all jobs on PISDINE are running from this community using a very, very small fraction of the node properties there. So, and we provided them a separate file system because, like I said, Lustre is not friendly to them, or they are not friendly to Lustre. So what did we do for that? How we created these abstractions that helped us providing this view. And there were a lot of things, but 3 things I highlight here because we in some sense leveraged what cloud technologies were bringing us in a general sense. And one could argue whether container is a cloud technology. So we used containers for them. That was really a deal breaker. Without that, it would happen. Although I have a picture of Docker here, but we used an HPC version in their environment. PISDINE, and like many other scalable systems, they do not have disk on the nodes. And we use some fabric attached network and other to circumvent that. We, in fact, in 2016, when we upgraded PISDINE, we took some of the requirements into their consideration for designing the system, which in the end helped some data science applications, which you see here, computing nodes connectivity. So we provided web service access to PISDINE. So you see some nice pictures here. However, if you want to take it further, let's say to another middleware or to data science, machine learning workflows, this is not the way to go. The reason being, it was more than a 2-year effort, and it is quite resource intensive in terms of time we needed from experts and continuous tuning and mapping. So if we go by this scale, of course, next time it would not be that long, but it is not automated. There are no standard mechanism and interfaces that I can go to a next customer who wants to map, let's say, their machine learning, deep learning workflow and say, okay, there are these APIs, go help yourself. We are not at that scale by any stretch of imagination. So yes, PISDINE is very friendly to the great middleware thing through all this hard work, but this cannot be completely translated to other communities and environments. So what do we do? And when we think about it, we say, okay, how we can empower other users and customers who would like to go beyond the model of, like I said, SSH, SBATch, and in that case, where they and us, we do not have time and resources to go through the same exercise as we did for high energy giving community. So I sort of looked at it, what does friendliness of an environment or familiarity, I should say, mean? And I said, it depends on your experiences and expectations. For me, HPC is as friendly as it could be because I was always in this area. If I don't do SSH, I don't know what else would I do in my life. I mean, in some sense, or write a job script. So for a majority of our traditional user, it's as friendly as it can get. I mean, nothing wrong with it. So I call them classical HPC user. I mean, I think if we do not provide those friendly interfaces, it will become unfriendly to them. So one of the key requirements for us is whatever we do to empower these other users and user experiences, that thing has to stay, meaning that the traditional accesses. Because we have so many GPUs in BizDyne, we had also experienced how some data science users want to use our HPC system. And there, I put like Jupyter Hub as an example. We have this service, but it works like an HPC service. It doesn't work like an on-demand service. So we have some dedicated small number of nodes, but if you go and install and want to run on a Discrete and make it your job elastic, you have to wait in a batch queue. So for them, it's as unfriendly as it can get. And also, storage connectivity is really not what they are used to and they expect in their environment. So if you have a data science user, a batch environment and storage connectivity and storage staging is something that makes our current BizDyne system as unfriendly as possible. And then the third users are a set of users where they would like to have privileged access. And what does it mean? And I will go into an example. So we have now many workflows where people would like to run some VM services to drive their HPC workload. There is no way to provision a VM service on BizDyne, but you can easily imagine why. So we would like to work in this environment where I call this API for lack of a better mapping, where the users in those extreme data workflows coming from experimental facilities, they would like to have privileged access to our resources to help their users. And I will go into it a little more later. So it's not like a dilemma, but we have to somehow manage, in some cases, competing requirements. Of course, we want performance. So this is one thing we just can't compromise. Otherwise, what's the point? So this is our value add. We want interactivity, we want bespoke services, and we want on-demand. So classical HPC user, they would really like to have performance and scaling as a service, as I mentioned before. We have to keep the batch processing and those accesses, and we have to have access to very low-level tool change for debugging, performance tuning, and improvement. And we'll learn in the talks later on from DK and other how people are, very sensitive about their few microsecond latencies. And we have to keep that because this is our value add. We can't compromise that. So we are already friendly, but no matter what we do, as we did in the LHC on Prey project, we cannot compromise that. So if you're looking for data science high performance use cases, of course data science has many, many use cases, and if they are not high performance, they probably don't need to come to us. They want software as a service, so they really have use their frameworks, whether we call them TensorFlows or whatnot, totally out of the box, and they typically would like to have the most latest and up-to-date version, which in HPC environment doesn't happen, and they want big data as a service. So they want many storage backends, which we don't have right now. They want interactivity, they want elasticity, which we talked before. And the reason the last one is in green, because I will go into a bit more detail with a project we are currently doing with PSI. The third is extreme data workflows use cases. So here you have workflow as a service. What does it mean? It means that it's not about running one application very fast. It's about moving massive amount of data in some sort of time-critical manner and processing it. You want automation because we do not have any control of the experimental facility that sits many hundred or some 100 kilometers away from it. So we have to provide them some way of accessing their environment. And this is a privileged access, but we have to change some policies on our side. And need composable platform services. So we need, I call the cloud plus delivery model, And plus here is for performance. So we have to use some programmability of cloud, but while retaining the performance of high performance computing in a standard manner, not what we did for the LHC on Gray. I think I'm still good on time. I will run over time, but yeah.
Started early.
Yeah, I started early. It's good I had more slides. So Swiss Universities is a funding institution within Switzerland. So they funded a project with Paul Scherrer Institute, and their CIO, I think so, yeah. They chose this very, very long title. So services for large volume experimental data analysis utilizing supercomputing and cloud technology, that's self-evidence. Okay, it's a mouthful. So what is it about? And it will come back. So what is PSI? So it's a large-scale research facility. So it's kind of a sister organization to us. We do large performance computing instead. It's research facilities, this is kind of we did one project for them where we worked with them to store their data on our tape drive. And as you see, this is the archival storage for their free electron laser and lighthouse sources. Essentially what they have a local IT center on site. But the amount of data that they will generate as their new experiments come online is far more than they can accommodate. So either they build their own data center, which is probably not that cost effective. So the idea is we use our expertise and their expertise to help the scientist. So they are going to experience some really exponential growth in data. So we added a connection to them, we added storage to their part. And as you can see, some numbers, they are 120 petabytes and up to 2 exabytes. And they have some short to medium term targets and for the storage. So if you just look at from a data point of view, these are big numbers. But just take a moment and think about someone would like to move this data, and if you move it more than once, it's not very good, and eventually you would like to process it. I mean, most of the processing needs to be done online, and I'll come back to that later. So that's why this project is quite challenging in the sense that, okay, generating data is one thing. This is a high-value data in these experiments, but they not only have to figure out data generation and storage, but they have to figure out data processing at the same time. And that's why this project is funded. So just to give you like a cartoonish view of the thing. So if you start looking on your right here, so typically what happens is the PSI facilities are like our institute, except that when people get time on experiment, they are more or less a dedicated user in the environment. So like time on HPC systems, a user applies for what they call beam time from anywhere of the world. When users comes to the PSI site or runs their experiment, they are given a specialized system, and then they do their compute, they get their data on DVD, and they go back to their home institution for rest of processing, and that's pretty much done. After the upgrade to their experiment, the difficulty that they have is the time a scientist and researcher is using the experimental facility, the amount of data they will generate, there is no way they can process them. There is no way they can burn it on many DVDs or whatnot and take that with them. So their scientific IT service model at PSI has to be completely rethought for these new requirements. Someone tell. Smart system. So So what we did with them, and this is like the workflow on technology mapping you see in CSCS environment. So first thing we did is we said, okay, we need a dedicated connection with them. And what will happen is the PSI user will always be a PSI user. They will not become CSCS user because they are not in true sense HPC user. So if we are doing something online, the top part, their workflow will take data from experiment, submit job in a reservation service or in an orchestrated reservation service. They move data between, in some cases, the archive and the active repository, and then consume it on PISDINE. And there are many, many keywords there, but essentially, we have to provide them some access to take data that is stored on the tape drive from previous experiments and run on PISDINE. And then in online way, when they are running experiment and generate data more than they have computing capabilities to compute, they use scalability of PISDINE. And both models, in some sense, can work, but we would like them to work in an automated way. So what we did was, we went back to the drawing board and saw what we did with LHC on Cray, what we are doing with some of our OpenStack and other services, and what we can offer them. And we wanted to generalize what we are going to propose as much as possible. So on the top part, if I just use PSI as an example, so they have their existing users. They go to their IT infrastructure, meaning PSI IT infrastructure, and PSI IT infrastructure, they have a couple of scripts where they can submit batch jobs to CSCS environment. And it's totally customized. It's been like that for almost 10 years, if not longer, and people can use it as is. We said we need to create at least 2 levels of abstractions, but they have to be standard. So in the project we are doing now, which is the target for Salvadas, what we are going to do is they are going to make 2 of their platform. One is they call DAS and map onto CSCS cloud services. But as an interface to our IT infrastructure, we provide them what we call infrastructure services. And I list a few of them. So PSI would like to maintain their own identity and access management. I call it AI, authentication and authorization services. And they would like to provide a set of their resources in form of containers. So PSI is going to mainly work on platforms, and we will provide interfaces to our infrastructure services that map into our environment. And the goal for us is we make it as much as possible using compliant cloud technologies and APIs that any other community user can bring the workflows, not only in our and their environment, but other IT infrastructure. And you can look at it from a separation of concerns point of view, but we are also trying to leverage as much as possible open standard and open technologies because they exist out there. So this is what we are going to. So hopefully if HPC Advisory Council continues and I give a talk in 2 years' time, I should be able to share some updates, at least on the middle part of this picture. So about to finish. So what we are doing at CSCS and how it translates into some of Salvadas and some other project action items. Because we have other similar environment that I didn't mention. We would like to enable on-demand. In Salvadas, what we will do here, because we are not replacing PISDINE, or it will not suddenly from one day to another start looking like a cloud software-defined infrastructure platform. So what we will do is, so far, today, we have a reservation service where the workflow there involves privileged access. We would like to automate it. So a PSI user or customer can automatically use it. There will be some human in the loop for approval or whatnot, but in theory, it should be as automated as possible. So they will get an idea or a feeling of on-demand access to resources. And this will allow them to coordinate the time they get on the beam versus the scalable processing on this kind. They want bespoke services, so they have many of their local services, whether it's about user registration, whether it's about their own database, whether it's about their MATLAB service. They would like to bring a number of their VMs, in some cases as a backup or in some cases as a main service to our environment, so their services have faster access to our resources. And they would like to therefore have privileged access to VMs inside the CSCS environment. And secure web access, interactive. We at CSCS have to figure out at least two things. We would like to find out what is the proper interface for a batch and a service-oriented scheduling system. What does it mean? We don't want to have many idle resources just because someone might come and use it, but at the same time, we would like to have some policies where we can somehow suspend and resume a batch operation if something like that happens. We are far from it, but some ideas are there. So eventually, in this case of Salvadas, we would like to empower a customer who will then empower their own user. And there are many policy decisions to be taken. So, going back to my original picture, we are thinking of some kind of merging. And if I have a crystal ball and I were to look into future, we will, for the most part, retain our, if I can say it, HPC heritage. Because this is our value add to our customer. But we will very selectively use some of the cloud technologies to end up in the target. And what is our target? Our target is a software-defined infrastructure for performance, because we want to have some features of automation. And finally, this is something Dave and I put together. We had a kind of a very successful panel at last SC about cloud myth and misconception. So it's going to be a mini symposium type of workshop on Monday, and we are calling it Supercomputing. And there we are going to look at some of the topics, and it will be invited speakers. So if you want to contribute with a talk, contact Dave or myself. We will be reaching out to some speakers. So the idea is with this year we start with a half-day workshop, because at least I'm very lazy, so I didn't want to have a call for paper and whatnot. But if we get as good reaction as we had for our panel and a higher attendance, maybe then in the subsequent years we would make it like a proper workshop in that regard. And our goal for this workshop is how to retain the performance aspect, but how to also look at interoperability with multiple data centers or cloud. Because it's no use in some sense if we at CSS figure out something. I think we are much more effective if majority of our data center, the same way we provide access to our resources in the current model, have similar APIs or similar interoperable interfaces. And I think we as a community probably will benefit in a consistent way, empowering our users and customers, and keep our costs low. So with that, I think I'm more or less finished on time, but I had some extra time, so that was good.
Questions?
Yeah?